Okay, so really what today is like the start of a new chemistry life for you, okay? So I'm hoping to get up to quantum numbers before lunch, and then after lunch we will do quantum numbers. What we're going to do as well is there's a really good documentary called 100 Great Discoveries, which has super short clips. Again, in an attempt to help visualize some of these atomic theories. We obviously can't split atoms in this class, stuff like that. Okay, so get out your highlighter or underline or whatever so we can highlight the important points here. And don't judge my highlighting, okay? So looking at when we get to quantum numbers, that'll be the first sort of step in looking at how to describe and show an atom in a different way than Bohr-Rutherford diagrams, because Bohr-Rutherford diagrams have exhausted their usefulness. We needed them in grade 9 and 10 to say, okay, this is approximately where the electrons are, protons and neutrons are in the nucleus. We needed it to say how many valence electrons in general a column or group has. So you could easily look at where it is on the periodic table, figure out the trend for the crisscross rule and stuff like that. But it's really so much more complicated than Bohr thought. Okay, so we'll start at the beginning. With early atomic theories. It is a theory, and the reason it's a theory is because, unfortunately, atoms are kind of a dynamic thing. So even an electron microscope that James Hillier developed, that takes sort of a snapshot or a frozen moment in time. So to see an electron, which is tiny and so fast, to actually see it moving around right now is essentially impossible. So we still call these theories. They're not laws because they haven't been concretely proven. So we're going to scratch the surface of your new chemistry life today. When you move on to university, you'll take this even further and look at weird sort of things that can happen, how orbitals can overlap, and there's much more to this than even what we're going to do. Okay? So in the beginning, Greeks were considered to be, a source of knowledge. They said all matter was composed of fire, earth, water, and air. Then Democritus was a Greek, and he was revolutionary. So he said, you know what, there's more going on here than just those four ideas. He said all matter was composed of small indivisible particles that he called atoms, so the Greek word for atoms essentially, which we still use today. And then, unfortunately, if you're a history buff, there are periods in human history literally called the Dark Ages. And it's not like the sun didn't come up. That's not what it means. What it means is almost nothing was written down. They were fighting each other, very feudal. Who's the king? Who owns this land? Who's going to be my wife? All that kind of stuff. How far can I spread my empire? And very little was connected to science. Religious fervor was also a big deal. So the idea that there was something smaller than the naked eye, some people thought challenged the idea that God was all-knowing and divine. And so people were persecuted. People like Copernicus and Galileo, that now we look at as these revolutionary scientists talking about what was beyond the earth. They were on house arrest. They couldn't leave their house. One of the scientists we're going to talk about here lived in France around the French Revolution, unfortunately collected some taxes for the government, and was killed at the guillotine because he was connected to the government. So there were all kinds of persecutionary kind of things going on that had nothing to do with scientists, that obviously made people sort of hesitant to be like, I think I'm going to look at this a little bit further. Even somebody like Da Vinci, he was sort of seen as very radical, digging up dead bodies and trying to see what they look like and all that kind of stuff. Whereas now, you could, when you pass on, you can donate your body to science, right? People use that as a tool. So very different thinking. And one of the things that sort of dominated for a long, long time was alchemy. And what that means is essentially trying to make something from nothing. So what the compounds that were discussed first often have a common name. So something like hydrochloric acid, if you have a pool or some sort of water system and you have to change the pH, you could buy something called muriatic acid, which is really hydrochloric acid. It just has a common name because it was so used at this time. Why? When you put a metal with an acid, you get bubbles, you get gas, it looks exciting. They could see that and they knew something was happening. What they didn't know was that all you're doing is rearranging the atoms. You're not making something else. So they were convinced that they could change something like lead, which was black and sort of ugly and soft, into something like gold, which was always in high demand, or silver, something shiny, worth money. So there were many flaws, but they believed that metals could be changed into something else. Really, really, again, not in the interest of science, really in the interest of making as much money as possible. So even early scientists who are considered to have made laws, like when we did gases, we talked about Boyle's law. So he actually did lots of things, but in that unit, we attributed him with discussing and figuring out the relationship between pressure and volume. But he worked with gases and did plenty of things with changing the volume and how that affected pressure. And that's a law, so that's a big deal. But he believed in alchemy. So, good and bad, right? Okay, there was lots going on. So it took a really, really, really long time in order for new thought to be had. Actually, let's just go back for a second. So what are we going to highlight? Democritus is we don't believe in alchemy anymore, so highlight this point here and do a better job than me. Okay, so we skip a huge dark age chunk of time. So the late 18th century, like the 1700s, then they started to do some quantitative experiments. And some people will consider Lavoisier to be like the father of that sort of movement. And so they did simple experiments, but used them to prove that mass was neither created or destroyed in a chemical reaction. So making careful measurements of how much reactant you have and how much product you get. They still didn't know, or still hadn't really even thought about molecules or moles or anything like that. So they're still just looking at reactions that were easy to see with your eye and manipulate. Something like combustion. So combustion experiments, obviously, they gave off energy. We could see that humans have exploited that, like the creation of fire creation, for years, right? So he showed that oxygen was required for combustion experiments. If you're a biologist, you would have probably talked about a man called Priestley. So he looked at putting something in a bell jar, and which involves like creating a seal, and then the candle would go out, and then he put a plant in with that candle, and of course now we know plants make their own oxygen, so it kept the oxygen inside the bell jar and the candle didn't go out. So he's also important with oxygen in a biology way, sort of more. So Lavoisier is considered more on the chemist side. So he is attributed with publishing the first chemistry textbook, but then he was killed in the French Revolution. So, didn't escape that. And then, but essentially proved the law of conservation of mass. Then somebody called Proust proved the law of definite proportion. So even though they still didn't necessarily say things like H2O, they knew that in a water molecule, no matter where you were testing it, again, sort of in Europe, Italy, Spain, England, Greece, like still that area, no matter where you tested water, there would be 2 parts hydrogen to 1 part oxygen. Okay, so the same proportion. Ooh, what are we going to highlight? So the law of conservation of mass and definite proportions we would have talked about before, but let's highlight those. I'm not going to ask you who was killed in the French Revolution or anything like that, but certainly, it's probably something you'll remember, I would imagine. So what you'll notice after these initial scientists, there was kind of a big spread in where people were. And then starting with Dalton sort of took the ideas that were kind of already there and took them together and coalesced them and made an atomic theory. And then, Thomson, then Rutherford came along. Rutherford was a student of Thomson. Bohr, took Rutherford's ideas a step further, so that then they started to really sort of work together or work in competition with each other. But as you know, sometimes people will use the word healthy competition. That kind of idea of a scientific community started to be built. Okay. So if you're into the history of science, what you'll notice is, say Lavoisier and Priestley essentially did sort of had the same result. They found oxygen or discovered it. They looked at how it was required for life, etc. But they had no real connection to each other, where now it tries to be more like a community, which is important. It makes scientists' life a little easier. Okay, so then early 1800s, we have John Dalton. And we use this fancy word postulate. It just means the 4 points of his theory. Which again, sort of looks, I don't want to badly highlight each point, but put a box around it or however you want to highlight it. So again, he kind of took a whole bunch of ideas and made it useful, okay, for the time. So he said each element is made of tiny particles called atoms. So drawing in Democritus's idea. He said that atoms of a given element are identical. Atoms of different elements are different, but he didn't say how. So he didn't know like the number of protons were different, etc. He just knew, obviously, oxygen gas was not the same as carbon, which we're made of. You know, like he knew that, but he didn't really say much about why. Chemical compounds are formed when atoms of different elements combine with each other. And so he took definite proportions kind of a step further. And we're going to talk about this idea more in organic chemistry. That there are certain elements that combine with the same simplest ratio. And we sort of talked about this in grade 11. We did empirical formula and molecular formula. So empirical formula was the simplest ratio, and molecular formula was actually how many atoms there were in a compound. So this doesn't really apply to something that follows the rules really rigidly, like an ionic compound. This would be more like glucose and ribose have the same empirical formula, but a different set of atoms. So glucose is a large sugar, ribose is the sugar in RNA. So this applies to really a specific type of compound. So he was more interested in not only do we have atoms, but we want to make them into compounds. So chemical reactions involve changes in the way the atoms are bonded together, but not changes in the atoms themselves, which now we know, well, electrons are shared, electrons are transferred. That's not really true either. So he didn't know anything. He basically had his model was essentially a featureless sphere. He didn't say anything about what was going on inside. No protons, no neutrons, no electrons, no quarks and neutrinos if you're a physicist, like nothing. So very, very, really similar to what Democritus said. So then as they could do experiments that were a little bit more intense, then they started to discover charge. So electricity is such a big deal because people then recognized how that could be used to, manipulate the body. It could even be used to split water into hydrogen and oxygen gas. We can do a whole section, a whole unit on electrochemistry. So once they discovered that stuff had charge, that was a big deal. So then that meant that something more was going on in the atom than what Dalton said. So J.J. Thomson studied electric charge with a cathode ray tube. And we're going to watch a video when we're all done about his simple experiment. And basically it was a gas tube, and he shot a beam of particles and had a magnet. So magnets have charge, and the beam of particles was attracted to his magnet, which meant it couldn't be neutral, or something about it wasn't neutral, okay? Okay, so his experiment, if he held a negative electrode towards the beam, it repelled because like charges repel. So he said the beam must have had some negative particles. He called those negative particles electrons. Overall, it was known that the atoms were neutral. So he said if there were negative charges, then there had to be positive charges as well. But he didn't really try to quantify them or anything like that, okay? Like how many, sorry. Okay. So sometimes his model is called a plum pudding. Plum pudding is like an old school British dessert. So if you don't have any experience with that, that won't make sense. If you watch the Tim and Moby about this, they call it like cookie dough. or chocolate chip cookie, which makes a little bit more sense in a mainstream way. Basically, the majority of the atom is positive, and the electrons, there are electrons, but they're stuck. So they didn't move. So like Bohr's orbits. No, he didn't talk about that. He didn't talk about the nucleus with the neutrons. He said it was like a sphere of positiveness, and the electrons were stuck inside. Okay? So this is positive, this outer part, and then the electrons are stuck. So the word I used here is embedded, which just is fancy for stuck. Embedded, can't move around. Okay, so then other physicists, like Millikan, he then could do he started to do experiments. He's like, okay, if there's negative charges, then that makes sense, because like I said, they were very interested in electricity and what was happening with that. So he wanted to figure out the charge carried by a single electron. So Millikan determined the charge So even though we say -1 is the charge on an electron, that's like the relative charge to a proton. That's not really how many volts the electron has as a charge. It's a tiny, tiny number. So then the idea that electrons had a certain amount of volts could then be exploited. Then we could make wires, and the electricity, the voltage could be conducted through it. So you can imagine how many times you plug something in a day, turn on a light, something electrical, right? So this was, I think he got the Nobel Prize, I believe. Does it say that on here? Yes. So he got the Nobel Prize. Okay, so this was a humongous deal. If you're in physics, you might talk more about his famous oil drop experiment that he used. We just need the one piece of that here. Okay, so then now we've got some positive charges, we've got some negative charges, and along came Rutherford. Yes? So another big discovery was radioactivity. So electricity, which is energy, sort of sparked the idea that, hey, maybe these elements have some, energy values to them. So what they did was they noticed that uranium, essentially, like an X-ray, kind of made a mark on a piece of paper without anything attached to it, which is, of course, radioactivity, which we now know is very dangerous. But the early scientists, hadn't considered that yet. But it was vital for the rest of the scientists. So Becquerel is attributed with first looking at uranium and discovering radioactivity. Sometimes the amount of radioactivity, say measured by a Geiger counter or whatever, like that kind of idea, is measured in becquerels, sort of in an old school way. Marie Curie, of course, and her husband were vital in the experimentation with radioactivity, which killed her. Essentially, she died of leukemia attributed with radiation sickness. Again, they just didn't know what they were dealing with. So what they did was, this says radioactive source, and they shot a beam of particles at a piece of gold foil. Okay? So sometimes Rutherford's experiment is called the gold foil experiment. And the gold foil experiment essentially disproved Thomson's idea. Okay? So Thomson said the atoms should be uniform. So then if you have a beam of particles and you shoot it at an atom sheet, then what happens on the other side should be the same. They should either all go through, all, come back at you or whatever. Uniform means the same, okay? So what actually they saw was all over the place. Some particles went straight through, some went to the right, some went really far to the left, some did come back, not uniform at all, okay? So this is one attempt to make a diagram. There are others that are bigger here as well, okay? So we're going to pretend like this is the gold foil, okay? If Thomson was right, that's what's on this slide, okay? So if Thomson was right and the atom was uniform, when he shot the particles, he should have seen them essentially go straight through. They look the same as this side. They go in, they come out, right? If he was correct. But that's not what they saw, okay? This is really what they saw. So we call the kind of radioactivity they used alpha particles. So some particles have very large angles of deflection. Some go through undeflected. It was all over the place. Some come in, some go out, some come back. So his two big conclusions, if you had something come back at you, that meant it must have hit something massive and turned around, right? If it went through with very little change in its path or deflection, then they must have hit almost nothing. It wasn't uniform at all. So let's highlight those down here. So still, even Rutherford, and you think about hundreds of years later, we teach you Bohr-Rutherford diagrams, right? He has not seen an atom. He has no idea. He is basing his theory on what he observes in terms of behavior, okay? So now we're gonna blow it up even further. So if this is now one atom, this is a diagram according to Rutherford or his model, okay? So some of the electrons went through empty space, some maybe we're lucky and hit an electron, some hit a nucleus, and the atom is not uniform at all. So he said the massive part of the atom it hit, he called that the nucleus. And he said that's where the positive charge was, which is the majority of the mass of the atom. We still use this idea today, right? We put the protons and neutrons inside the nucleus. And then he said the majority of the atom, though, is empty space. Okay, and you can travel farther down the physics rabbit hole and really get into the forces and what's really going on in quarks and neutrinos and all kinds of stuff. But we're just going to stick with protons, neutrons, and electrons, okay? Okay, but obviously there were problems with his model. So first of all, why in the nucleus did the positive charges not repel each other, right? They had seen repulsion in electrons, so why was there not repulsion in the nucleus? They could, if you look, which we talked about in grade 11, we'll talk about, or we'll look at again the mass spectrometer. So they had equipment now that could measure the overall mass of the atoms, and it wasn't just the number of protons. Actually, this should be, hold on. Changes to electrons. This shouldn't be neutrons. Sorry. And then the last 2 points really is where Bohr comes in. Okay, so if the electron was in motion around the nucleus, moving, then eventually it should lose energy and crash into the nucleus. Why doesn't it do that? And what they could do now is they could split light. So one of the first concepts of science you probably learned in elementary school was what's in a rainbow, right? Red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. Probably you watched the Roy G. Biv, Bill Nye, yes? So that was easy to do, okay? They could easily split white light into these different colors and basically look using this, what we call a spectroscope, a tool that can split light, that they could do this with beams of elements. So Bohr's experiments said there has to be more going on than they're just in motion. What does that mean? The electrons must have a quantifiable amount of energy. And that's really what quantum mechanics and all that kind of stuff, where that comes from. You can't just say, oh yes, this is where they are, this is how they behave, we need more, okay? What are we going to highlight? You know what, we'll just highlight the title and hopefully that helps. Okay, so we talked a little bit about mass spectrometry in grade 11. How do you figure out how much an element weighs? Well, spectra is really just a graph with lines. So basically taking a sample and changing its mass into a graph with lines, which is simplified on the next slide, so I'll show you in a second. And it's really basically a really basic idea. If you have something heavy and you try to push it, it's going to go less far than something that is light. You have to give it very little energy and it goes way far, right? So based on mass, we could separate atoms in a really simple way. So then that helped us to discover something called an isotope, which is some elements have the same number of protons, but they are heavier. So there has to be more than just protons and electrons. But basically, essentially do nothing else. They don't contribute to charge. They don't influence its chemical behavior. Okay, so the whole premise is here. The most massive ions move the smallest amount, which makes sense. You could even use a cheesy analogy with people. If you know somebody big and you try to push them, do they go far? You know somebody small and you push them, they probably would fly across the room, right? Okay? It's the exact same idea. Not that I am encouraging that. Okay, so what the mass spectrometer does, so if a beam of particles comes out of it and they make this line spectra, okay? So you don't have to do this. I'm not going to ask you to create this graph, but it will create a graph. And the lines have different thickness and different height. So then mathematically we can say the relative abundance, if you guys remember that from grade 11, and doing that calculation, which we don't have to do this year, okay? So if you get 3 lines, so for example, carbon, because carbon is us, it's everywhere, all living things, or things that were alive, there are 3 isotopes of carbon, carbon 14, carbon 12, and carbon 11. You talk about half-life, usually talking about carbon dating in math, okay? So how much carbon is left in bones and rocks and all that kind of stuff. This is based on that idea, okay? So we don't really need, this is just to show you how they did it, how they quantified it, but we don't have to make any highlights on there, okay? Chadwick, though, he is attributed with experimenting to discover or first describe what a neutron was. So he again used radioactivity. He used beryllium and then the stream or the beam of particles that was released was not affected by negative field like Thomson's experiments were, which meant it was neutral. So as much as the nucleus had protons, it had to have something else. So he called that something else neutrons. And we exploit this. So in grade 11, we talked about using isotopes for cancer treatment or using isotopes as a way to do medical imaging and stuff like that. So there is a different nuclear stability, like some nuclei will break down, half-life, which you calculate in math. If you find a dinosaur bone, you can't be like, hey, dinosaur, when's your birthday? But they can calculate how much carbon-14 is left and using the half-life in order to figure out how long ago that dinosaur was alive, that kind of stuff. And all based on the number of neutrons in the nucleus. Okay, so now on to electrons. And electrons, of course, the movement of electrons is really what chemistry is all about. So there were plenty of scientists, again, across Europe, and depending on what kind of other courses you take, you would talk about Planck and Kirchhoff and Einstein in physics as well. So they did experimental studies on the interaction of matter with electromagnetic radiation. So famous experiments like black box radiation. Max Planck is considered, like H is Planck's constant. Hertz was in there too, like Hz which is what we still measure radio waves in. Interesting though, Planck and Kirchhoff and Hertz were die-hard Germans, World War I, and then along came, and they fought in the front lines. Then along came Hitler, and they were Jewish, and they were persecuted by the time of World War II. So then the scientists sort of fled to America, where they weren't persecuted for who they were. So again, sort of a tumultuous time in science. Okay, so they did a lot with light and energy, and the big thing at the time was, is light a particle or a wave? So again, if you were or took physics, you talk about that quite extensively. Okay, so those of you that were in physics, did you talk about this? Yes? Those of you that are in advanced functions, calculus, you draw sine waves and cos waves. Yes, like this. Those of you that took biology, you talk about photosystems and light coming in and exciting the electrons at a certain nanometer. So light and energy is everywhere. This was revolutionary and touched all areas of science. So important, okay? And also created a little bit of butting heads. Schrodinger and Einstein, two famous scientific names you may have heard of. They really fought about are electrons a wave? Are they a particle? And then in the end, they basically said, who cares? They're both. Okay, similar to what they did with light. So if this interests you, then maybe you would like to take more physics. In university, you could take quantum mechanics, which is usually under the chemistry umbrella, but also is sort of applied math and applied physics. Again, it's much more, you can go way, way, way more in depth than we're going to do, okay? Because I feel like there's already too many names in this slideshow already, there is another man who is considered to be part of these important experiments called de Broglie. So if you've heard of him, you know, but we'll just keep what we have, okay? So electrons were thought to move as particles, similar to light. And then Let's talk about them as waves. And the big idea came to a head no matter which way you did it. The idea that electrons were packages of energy which could be quantified was also revolutionary. And Einstein called electromagnetic radiation, which of course, you know, instead of red would be like 450 nanometers, that kind of thing. He called that photons. And you think about things associated with light, photosynthesis, photography, right? All of that stuff stems from this word. Okay, so each color of light has a certain frequency. And then we could even, you know, things like infrared, which was like heat signatures, stuff that we can't see with the naked eye, UVA, UVB, X-rays. It's like a whole spectrum. So we teach, you know, little kids about Roy G. Biv because that's what we can see. Okay? But there's lots more energy out there. Okay, so because light has a certain frequency and a certain energy, and then we could do really simple experiments where it seemed like the elements themselves were producing light, then they connected, okay, then electrons have energy, also light, it all sort of was coming together. So in grade 9 science, if you had it in school, you might have done, well, we did some in grade 11, I think, the flame tests, where you dipped it in and put it in and saw the color. A very simple experiment. We heated it up, we gave it energy, it made light. That light is energy from the moving electron. Too excited. And that's really what formed Bohr's ideas. So again, he took this whole, you know, generalized idea about electrons and light and energy and really tried to apply it to the atom. Okay, so this is old Bohr. I just kind of put it as a watermark. If it didn't show up, that's okay. So he was born close to the 1900s, and he expanded on Rutherford's theory. So again, a scientific community. And he said electrons didn't travel randomly. He said, no, there has to be orbits. Okay, so in the first orbit, what do you draw in your Bohr-Rutherford diagram? How many electrons? 2 in the first, 8 in the second, right? That was Bohr's idea. Very, very specific. The outer orbits, like as you've got farther from the nucleus, they held more electrons. Even this idea today we still use. Outer orbits determine the atom's chemical behavior. Atoms emit light when the electron moves around, which you guys, right from grade 9, we can do a super simple experiment showing that, okay? And he got the Nobel Prize. I'm never going to ask you like, when was Bohr born? You don't have to worry about dates, just to give you an idea of the timeline. That's why I included them, okay? I forgot to say that at the start. Okay? So this is the birth really of quantum mechanics and connecting it to atoms. How can the behavior of electrons be quantified or given a numerical value? So, but unfortunately, he did his experiments with hydrogen, which is fine, except hydrogen is very simple, right? So, you know, of course his experiments worked with a simple atom, and then once you moved away from hydrogen on the periodic table, things really started to fall apart, okay? So he he did lines, he made a spectra, and used hydrogen and helium as well. So again, a super simple element. And you guys are going to do this next week. You can, even with our very rudimentary spectroscopes, you're going to look at different tubes of gas and you'll see different lines. So he said that, or he did experiments, and the elements had unique spectra, which meant that the element's electrons had a unique amount of energy. So this unique amount of energy meant they didn't have to stop moving or crash into the nucleus. They existed in their very specific orbit. So I'm just going to, just to not have to highlight like a maniac. Electrons do not give off energy or radiate energy as they orbit the nucleus. So you might see words like stationary state, which is just sort of the normal condition. And he was very specific. The electrons hang out in the specific orbits. The first orbit, 2. Second orbit, 8, right? He was very, very specific. And really sort of flat thinking. In order for electrons to move around, you have to give them energy. So what did you do to give them energy? You put it in the fire, okay? Fire is energy. And then when they absorb the higher energy, they move. And when they fall back down, because you have to give energy away, you see that light, like us. We see the light. Copper gives off green light because its electrons have different energy than probably we did strontium, which is very red, potassium, which is like a pinky purple. Okay, so you can see different colors because of the different energies. So here is, this is young Bohr, if you care. But so here's his nucleus, and unlike Rutherford, which is electrons moving all over, he said no. The electrons travel in these very, very flat orbits. Okay, so central nucleus, allowable energy orbits based on energy that the electron has. Which, again, more if you take physics, you would calculate energy with Planck's constant and frequency. We don't need to do that in grade 12, okay? But you know all these words: allowable energy orbits, lower in energy is closer to the nucleus. You would have talked about that right from grade 9. And really, we still draw Bohr-Rutherford diagrams today. Well, up till today. Okay, so this is just a picture of what a spectra would look like. So I can't photocopy color. Don't worry about the color. This is what you're going to see next Tuesday or Wednesday, I forget which day. It'll look black, and then there will be these lines of color, and you'll see those even when we use these simple spectroscopes. So this is even evident in a rainbow. The water in the air is splitting the light coming from the sun, and you're seeing Roy G. Biv instead of white light, which is all combined. Okay, so it can be done simply in a simple way, as Bohr did. We'll talk about what N is again, but this would be like the first shell is called N, the second shell is N equals 2, third shell is N equals 3. Things like The first row of electrons have one shell. Those kinds of things still, those patterns are still important. Okay, so how was he successful? A big thing here was it accounted for the stability of atoms. So you didn't have to worry about the electrons crashing into the nucleus because they hung around in their standard state or stationary state. It was really good. They could find a sample of gas, they didn't know what it was, and look at the spectra and match it to hydrogen. That was wonderful. You know, you're getting reproducible results. Isn't that great? And if you had very, very simple atoms and ions, it was beautiful. But of course, there's always exceptions. Okay, so really he was just a victim of his equipment. So his equipment, much like ours that we're going to use, was just too simple. And once they could use more precise techniques, lines that he thought were one line, so one orbit, actually could be split into many more orbits or many more lines. So, so not a single energy level, but a group. So there had to be modifications introduced, including electron spinning, which is what is going to lead us to how we're going to represent the atom moving forward. Okay? So the next diagram, again, I know it doesn't print in color, but that's okay. What the next one is trying to show you is the idea of the single could actually be split apart, okay? So he would have said, for example, he would have been like, okay, n equals 1. That's all that's there. That's all I see. And then when they got better spectroscopes, then they noticed, well, no, there's these faint ones here that you couldn't see, and this fat one is actually 1, 2, 3, 4, 5, 6 lines. You were wrong, okay? So how can we represent 6 lines? How can we, without having to do this every time, or drawing this super complicated Bohr-Rutherford diagram? So we needed something else. So what the something else is going to be the quantum numbers and what we do tomorrow, okay? Okay, so we are going to move away from an orbit, and we're going to use the word orbital. So what's an orbital? It is a 3D space. We'll talk again about this, but each orbital can have 2 electrons. Might as well get used to that today. So it's the greatest, the probability that electrons can exist in this region of space. Electrons are so fast and so small, it's impossible to say, nope, they're right here on this flat orbit. No, that's just too simple. Okay? So again, we are going to try to move away from what Bohr thought, his flat idea about how electrons traveled, and switch to trying to represent an atom that makes a little bit more sense. If electrons are so small and so fast, how can we say, no, they're in these flat orbits? And really, his experiment really started to fall apart and you just couldn't anymore, okay? Especially as they started to get more complicated equipment. So the first way we are going to look at to try to represent atoms without drawing Bohr-Rutherford diagrams is the 4 quantum numbers, okay? So what we need to do, I'm just going to skip ahead, and I just want to show you something. So the very last picture in your package here is this crazy picture here. And you might be saying to yourself, well, it didn't photocopy very well. And that is A-okay, because imagine if I said to you, okay, you need to draw, we're not going to draw Bohr-Rutherford anymore. We're going to draw what the atom really looks like, the electrons occupying 3D space. So this is trying to represent a sphere. The next complicated shell, sometimes people call them dumbbells. There's really, you're used to X and Y. Z is the axis that comes out at you. So here's a dumbbell here, dumbbell here, dumbbell here. You get a little bit more electrons. You need to draw some clovers. This one kind of reminds me of a soother. As if, right? Does anybody want to draw these? No way. Okay? So what are we going to do instead? We are going to use numbers and letters in order to represent atoms. So the first thing we're going to do is the 4 quantum numbers. Then tomorrow we're going to look at electron configuration and energy level diagrams. So like I said, it's kind of a continuum, and it's all going to go together. The 4 quantum numbers sort of are like the base. It's even though it's still 4 numbers we're going to use, it's still a little bit too general. Electron configuration and energy level diagrams you could do for specific atoms and ions. A little bit more straightforward than this, but this helps us form our basis, okay? So the sorry, I just have to move this a bit here. Here we go. Okay, so the principal quantum number it's a positive whole number, and this number is what Bohr would have said, and he just didn't call it the principal quantum number. Basically, it corresponds to the row on the periodic table. So n equals 1, row 1. N equals 2, row 2. N equals 3, row 3. And in order to do questions about the quantum numbers, really you have to be given this. So usually you're given the n value, and this describes Bohr's main shell of electrons, okay? So positive whole number describes the main shell of electrons, and Bohr thought the higher the n value, means you can correspond that means more energy, and it also means that the electrons are farther from the nucleus. And that was one of his successes. That was true, yes. Okay, so the main shell still corresponds to the distance from the nucleus. So he was good with that. And like I said, when you do questions, you are usually given this number to kind of guide you, where is this element? But as you can see, depending on what row you're in, there are quite a few elements. So describing an element by its n value isn't so useful. It's not so unique, but it forms a good basis for us. Okay, and then the second number. Now, sometimes we try to use a funny cursive L. It's like a lowercase l. But because L is, it's hard to tell, is it capital I, is it L? Sometimes we'll use a cursive font. So this is going to describe what we call subshells. And what's a subshell? So what this means is, so Bohr would have said n equals 1, 1 flat orbit. N equals 2, 2 flat orbits. But at that n value, when they could split that spectroscope line into more lines, then they saw 3 lines instead of 1. Or when we do the clovers and the soothers, that's 5 lines instead of 1. Okay? So it's like the subshell, it's sub to the principal energy value, or it's limited by the principal quantum number. So that's kind of why the question starts with this, and then everything goes off of that, okay? So when you are asked about the L value, down here is what you're going to do. You're going to start at 0. And go up to n minus 1. So if you have n minus 1, then the L value is only going to be 0. If you have n minus 2, then you can have 0 and 1. N minus 3, you can have 0, 1, 2. N minus 4, 0, 1, 2, 3. Okay? So you can't go higher than n minus 1. And what does the 0, the 1, what does that mean? Instead of drawing a sphere or those crazy dumbbells, what we're going to use is this number, okay? So the last sheet in your booklet on the back has a summary, okay? So we're just going to do, again, we're just going to do the fundamentals for a second, and then we'll do a summary, a bunch of summaries actually. So L is 0, that's a sphere. We call that S. When L is 1, we call the orbit polar because it's like on all 3, X, Y, Z, or we use the letter P. When L is 2, it's going to be D. When L is 3, it's going to be F, or fundamental. So if you have done any of your own delving into physics and quantum mechanics, then you might have heard of SPDF. That's what we're moving towards, instead of drawing this or drawing Bohr-Rutherford diagrams. So in this number, and then tomorrow this letter, are going to represent this shape. This number and tomorrow this letter represent this shape. Because it doesn't matter. Is the electron here? Is the electron here? Is the electron on the back? Who cares? Too fast and too small. So we can just use a broad number, a whole number, to represent this probability of maybe where we're going to find the electrons. Bohr was much too specific. It has to be right here. No, that's not a thing. Too fast and too small. Okay, so let's say this one's boron, I think. So if we were going to draw a diagram for boron, you would have to draw a small sphere. Then you would have to draw a bigger sphere. Then you would have to draw a P. But then you would also have to draw other P's because maybe the electrons could be in there. What? No, we're going to do this. Okay? And the wonderful thing about this is the periodic table. So you saw the video with Mendeleev basically like playing cards. He figured out the periodicity, and it works for this as well. Okay, so once they really could describe how many electrons, how many protons, then it fit what he had already predicted. Which is, of course, what you want in science, right? Reproducibility. Okay? So then they also had to consider what was happening once they started to use electricity and charge and magnets, like what you saw Thomson do, or, well, a representative of Thomson. And again, this can get much more complicated if you take more physics courses. We are going to do the magnetic quantum number, or ML. And this comes from, sorry. So M with the little L. So again, it's trying to show it cursive so it doesn't look like an I. So trying to give a number to how many lines they saw. So Bohr would have seen one line, for example. Once they could do better spectroscopy, then the one line actually was 1, 2, 3, 4, 5. So we don't want to draw spectra, so we're going to use numbers. Oh, there it is. So once you decide what the L value is, then the ML value, the way that we quantify it, is a range. So it's like you're back in, grade 5 and you're making a number line. So if L is 1, then start negative. Negative 1, 0, plus 1. L is 2, negative 2, negative 1, 0, plus 1, plus 2. Okay? Just make a number line, basically. Okay, and then this one is the easiest. Again, because electrons are too small and too fast. So all we can say, we cannot say this electron in part of the pair is spinning clockwise. This one is spinning counterclockwise. So you're going to put plus or minus a half for MS every single time, because that's all it can be. One electron, sometimes it's called spin up and down. One electron will be spinning up, is considered to be spinning up. One electron is considered to be spinning down. How can electrons pair up if they're the same charge? Why don't they repel? Well, if this magnetism is true, this spin, then it's a way to rectify that. If they're spinning in an opposite direction, then maybe they're not repulsive as much. So this chart just goes through the same thing again. N value is a whole number, which you have to be given. Then you do L up to N minus 1. ML is the range. And MS, all you have to write is plus or minus a half. Okay, so let's do an example. Oh. Okay. Yeah, it should be. Is it? Yep. Okay. So, like I said, for the principal number, you really have to be given this. And normally, if I was going to give you this kind of question on a test, then the chart would look similar to this. So if we have an N value of 4, that means that you're going to get 1, 2, 3, 4 secondary values. So the number of rows you can use as a clue, okay? So how do we do the L value? You start at 0 and go up to n minus 1, okay? Every single time. So there is not a lot of variety to this. So again, that's why you're going to see what we do tomorrow is much better, much more unique, okay? So my n value is given to me as 4. I start at 0. 0, 1, 2, 3. Well, how come I stop there? Oh, yes. I'm limited by n minus 1. 4 minus 1 is 3. Okay? It doesn't really matter when you write the range if you start with the positives or negatives on the left or right. Normally in math, we do negatives first, and then we go to positive. So that's usually what we do, okay? So now I already have the rows here. I've already got my L value. Is there positive or negative 0? No. So all we have is 0, okay? My L value is 1, negative 1, 0, plus 1. My L value is 2, negative 2, negative 1, 0, plus 1, plus 2. My L value is 3, negative 3, negative 2, negative 1, 0, plus 1, plus 2, plus 3. My range is too long, but that's okay. Okay? So this doesn't tell me anything about what element we're talking about. If this is 4, that means 1, 2, 3, 4, period 4. Look at all these elements in here. There are so many. Okay? So this is a good beginning start to not having to draw the diagrams, but representing the shapes. But it's just not useful enough, so we're going to switch tomorrow. But this one here is about as specific as you can get. As you can see, a lot more numbers, and you'll see what happens, okay? So this one, sometimes on the test, I'll actually merge this because really, what am I going to write here every single time? Plus, minus, half. Can I say which one's spinning up and which one's spinning down? No, I cannot, okay? So that's the best we can do. It's supposed to be a negative, sorry. So this is what Bohr would have said. One shell. Well, this one would have been 4. 1, 2, 3, 4. But they saw more lines, and it corresponds. So let's say you had 0, and their numbers are meant to follow conventions you already know. So you would think of 0 as first, then 1, then 2, then 3, right? So the same thing in an atom. So this would be considered first, and by first we mean close to the nucleus, okay? So over here, this diagram is obviously, that's simpler than this. You agree? Yeah? Okay? So this is 0. After 0 comes 1. In the row where L is 1, the next one, ML, how many numbers are in the range? Yes. 1, 2, 3. So now, again, we're just doing probability, but for simplicity's sake, we'll call this, oh, they already did it, -1, 0, and +1. Do we really know that like that's too specific, too fast, too small? We're not going to do that, okay? But there are 3 of them. Before I even do this, don't look at your other chart. Based on this, 1, 2, 3, 4, 5, how many should there be in the L is 2 in the range? 5, -2, -1, 0, +1, +2, 5. Okay? Then this one's going to be 7. -3, -2, -1, 0, 1, 2, 3. Okay? So these shapes we are going to represent with numbers because no. Even an artist like Callie doesn't want to draw these. Yeah? Okay? No, we're not doing it. Now watch this. So back on the slide that says, I think I made you guys highlight it. In an orbital, what's the maximum number of electrons? 2. Okay? So this is 2, 2, 4, 6, 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 12, 14. Okay? So this sticks out on the periodic table. Do you agree? Number 1 is the simplest element. How many columns are here? 2. What's next? 6. So we'll go next. What's next? 1, 2, 3, 4, 5. Oh, 6. What's next in here? I bet you it's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Without counting down here, how many do you think there are? 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? So the periodic table matched quantum theory, and Mendeleev, his initial organization only was based on properties. He didn't know about electrons, and it matched. Okay? So that's beautiful science. Yes? Oh, yes. So instead of drawing the shapes, we call this S because it's spherical. P stands for polar. Again, that's on the chart. Don't worry. I think it's because like these are kind of like poles, like one side, like the Earth, a magnet. These are called diffuse, and F for fundamental, but I didn't make it up. But that's going to be that's in this, I think. We can write it on this summary chart because you really never need those words, really, but that's what it represents. Okay, so let's go back and try to connect it to Bohr, okay? Because he wasn't wrong. Why do we, totally, if he was, would we teach you Bohr-Rutherford diagrams? Probably not, you know? So there had to be some truth to what he was saying. Okay, so he was in it to win it with the N. This was Bohr. Yes, he was good. His little formula, I guess, for the number of electrons was 2n squared. And I don't even think the grade 10 teachers teach you 2n squared or grade 9 anymore because it works for the first ones. 2n squared, 2 times 1 squared is 2. 2 in the first. It works for the second one. 2 times 2 squared, so 2 squared is 4, times 2 is 8, right? That works. You would have said 2 in the first, 8 in the second. But then we teach you 8 in the third, and then you just make another one, right? But if you had n equals 3, what's the maximum number of electrons, really? It's 18, right? 3 squared is 9 times 2. So why do we tell you 2 in the first, 8 in the second, 8 in the third? No, because we're fudging things so that you can see how many electrons are lost or gained. What's the name of a really simple compound going to be? But now you have big grade 12 brains, so we need to fix our model of the atom, okay? So again, if we have 1, so 2 times 1 squared is 2. It does say this up here, but if you want it to be in the chart, okay? So Bohr said that 2n squared described the maximum number of electrons. Okay, so then 2 times 2 squared is 8. So far, so good. But then when you get here, we do not tell you to put 18 in the third shell, right? So we have been, we have been modifying the truth for you in grade 9 and 10 and 11. No, let's not use that word. Okay, so let's see how this correlates. So the secondary number, you start at 0 and go up to n minus 1. So if n is 1, then we have only 0. If it helps you and you want to divide this table even further, draw like this. These two go together. I mean, that one, I guess. And then this goes together. Okay? So if we have n equals 2, start at 0, n minus 1 is 1. That's as far as we can go. We have 3, 0, 1, 2. Then you do ML. I didn't include MS here because who cares? Plus, minus, half, doesn't matter, right? Let's leave that out. Simplify things. We're going to do negative L to positive L. So we have 0, 0, 0, 0. Okay, so we just did this. So does the quantum mechanical model, how can it fit with Bohr? So this is where we need this part here. So I'm going to use red, okay? So 2 electrons in each orbital. So here we're going to do 2 electrons in each. So here we have one number. So that's 2 electrons, okay? Does that match with what Bohr said? Yes. Then we have 2 here. And then 2, 4, 6. Okay? Here I'm going to extend my lines. What's 2 plus 6? What's 2 plus 6? 8. Okay, we're okay. Yeah. Then down here, we want to fix this 18, which we've been modifying the truth about. 2, 2, 4, 6, 2, 4, 6, 8, 10. What's 2 plus 6 plus 10? Okay? So I didn't lying, we modified, yeah? We modified the truth. So the quantum mechanical model does correlate slightly with Bohr, but not his simplicity, not his flatness, okay? We're going to try to think in a 3D shape, trying to draw and represent on a paper pencil task using 3D shapes is very difficult. So this is really, really general. We're going to do more with the S and the P and the D and the F because the periodic table is a useful tool that we can use to help us do that, okay? So what I'm going to do is I will write on the board the, what's it called? Like the theory questions about the scientists, and then there's 2 categories, and then quantum number homework. What we'll do tomorrow, we'll talk about this summary sheet. So if you want to focus on just the scientists tonight and leave this for after what we do tomorrow, because it does really kind of go together, okay? If you're like, you know what, I got this, I want to give it a try, then try the quantum number as well. There should be more time in class tomorrow for work, okay?